Good morning. We are going to continue our discussion on chapter 3. To summarize again, in chapter 2, we discussed a lot about the electric field and the potential, and we calculated these for certain charge distributions, and then we have seen some general conclusions. And in chapter 3, in the last lecture, we started to take a more of a general approach, and we looked at the Poisson's equation, or we looked at Laplace equation. Essentially, the charge density is zero, then there is no term, source term, so that gives us this Laplace equation. This is what we discussed in the last lecture, and our goal is to use the Poisson's equation to solve for the potential, and once we find the potential, we know the electric field, and so that's why we wish to solve this differential equation. And to solve that, we have seen a couple of things in the last lecture. To give you a summary, we looked at harmonics. Harmonics are the set of solutions to the Laplace equations. And we looked at different types of harmonics like polynomials, logarithmic functions, or exponentially decaying functions, so on and so forth. So we looked at several harmonic functions in the last lecture. And then we proved a very, very important property of the harmonic functions, that is the mean value theorem. And we did this because we needed to use this for another proof, which I'll talk about in a minute. So we proved the mean value theorem, which said that if I have a region, right, in this volume, this del square phi is equal to 0, then if I have this point R, I can draw a sphere of radius R around it, and the value of the function at the center, that is phi at R, is simply an average over this surface area of the sphere. So that's 1 by 4 pi R square, surface integral of phi of R prime dr prime, where or dA prime, where this sphere is what you're integrating over. So this is the sort of the average over the surface S. So we proved this explicitly in the last lecture, and then we did so because we wanted to use the mean value theorem in terms with Helmholtz theorem. And the Helmholtz theorem is essentially that if I have a volume, let's draw another volume here. If I have a volume and I know I specify the divergence of a vector in this and the curl of that vector field, right? So is G of R, and then this is within V, within the volume V. So Helmholtz theorem states that if I specify, I'm specifying the divergence and curl over the volume, and then I specify the value of E on surface bounding the volume. So I'm defining E only on the surface. So divergence and curl are specified over the volume, and the boundary E is also specified. So if these three things are specified, then the Helmholtz theorem posits that the solution is unique. The solution to E is unique. So don't think that just because we are specifying it on the surface, it is unique for entire volume, because this value is only on the surface. So it doesn't say anything about the value inside here or value outside there. So by using this theorem, we know that unique solutions to E exist if you specify the boundary condition. And we proved this using the mean value theorem in the last lecture. So we essentially showed that if we have these conditions, then we can find E. So, and that's what we are going to use today to solve a very simple problem, so that you will see how we apply this. And so the problem that we are going to do today is that of a conducting sphere. And previously we solved the same conducting sphere using Gauss's law and Coulomb's law. But what we are going to do is solve the same example again using the Poisson's equation. So a brief review about the conductors, because we are going to talk about a conducting sphere. Recall that we have seen that the electric field is equal to 0. The total electric field is equal to 0 inside the conductor while discussing chapter 2. And we have seen that rho inside is 0 because all the charge goes to the surface. So that's another thing. So the net charge in a conductor lies on the surface. And because E is equal to 0 inside the conductor, that means phi is constant, the potential is constant, because E is negative grad phi. So that means the potential is constant throughout the conductor. If potential were not constant, then you would have an electric field, but we know that we don't have an electric field. And just outside the conductor, E is always perpendicular to the surface, right? So if I have a conductor that is like this, right, there is charge that is accumulated on the surface, all this negative charge, let's say, and so the electric field points to normal to the surface, right? So the electric field points normal to the surface on the surface of the conductor. So now we are going to use this and look at the problem for conducting sphere. So we have a conducting sphere. So let's draw a sphere here. So we have a conducting sphere, and let's say the sphere has a radius of r. So because it's a conducting sphere, all the charge is on the surface, right? The charge is on the surface. And so inside rho is equal to 0. And other than the surface, even outside rho is equal to 0. There's no other charge other than what is on the surface, right? And so we can see then that del square phi outside is 0, right? And del square phi inside is also 0, because the charge, there is no charge inside, or there is no charge outside. So what we are going to do is we are going to solve this problem using the Laplace equation, right? So del square phi is equal to 0 for both r less than r and r greater than r, right? So this is phi of r. So it's 0 inside the sphere because there is no charge, and outside also there is no charge. The charge is only on the boundary. So we have less than r and greater than r, and then we need to use some sort of boundary conditions to know what this phi would be at r. So let's see how to solve this. So let's start with these two, right? And you see that you have a spherical symmetry here because the charge is on the surface of a sphere. So you have radial symmetry. That means, if you were to rotate the sphere by a few degrees, it wouldn't make any difference in the sense that the charge distribution is uniform, and you see the same charge through any radial view. So the solution phi should have that radial symmetry. So we can say that this phi is entirely just made of r, no theta phi components because of the spherical symmetry. So we need to consider only the radial part of the gradient. Only the radial part of Laplacian. So the radial part of the Laplacian del square is 1 over r square d by dr, r square d by dr. This is in spherical polar coordinates. So we're trying to solve the Laplace equation for inside and outside sphere, and we made the argument that whatever the solution to this del square phi of r is equal to 0 because of the symmetry in the problem, because the charge is on a spherical surface, so it has spherical symmetry, and because of that spherical symmetry, we argued that phi would not have theta and phi dependence, and so phi would have only r dependence, so only the r component of the Laplacian is useful to us. So then we can expand this del square phi of r, and because we have only the r component, this would simply be 1 over r square d by dr, r square d phi by dr. And we know that this is equal to 0 because there is no charge inside or outside the sphere. So then this must be a constant because you're taking a derivative of that, and then you're getting a 0. So you can argue that this must be some constant, right? And so we can call this constant to be C0, let's say. Then I can write that d phi by dr is C0 by r square. So I can do an integration, right? And then I can get phi of r in general to be minus C0 by r plus some constant C1, and I can absorb this negative sign into the constant, and in general write it as CO by r plus C1, right? C0 by r by C1. So this would be the general solution for del square phi is equal to 0 for r less than r and r greater than r, because we have spherical symmetry here, right? So then we can write from here phi outside, right, would be something like C0 out by r plus C1 out, and phi inside would be C0 in by r plus C1 in. So these constants C0 out need not be equal to C0 in, and C1 out need not be equal to C1 in. Because this is for r greater than r and this is r less than r, we have not yet specified what the boundary condition is. So here we have a sphere, conducting sphere, which is charged on the surface. We know the potential inside. In general, this is the solution for the potential. That's how we solve the Laplace equation. Inside and outside, the charge is 0. So we have del square phi is equal to 0. And using the spherical symmetry, we made the argument that the phi is radial. And then from there, for the charge distribution, we have found out that this is a general solution for inside and outside, but we don't know what these constants are. And we can find out these constants by determining what should happen at r is equal to r and other places, like we will see, but mainly we will use this as one of the boundary conditions, as we will see. But there are also other boundary conditions. Let's see what they are. So now our goal is to determine these constants, what these constants are. So only when we know what those constants are would we know completely the potential, and we also need to include the boundary. So let's see what to do there. So let me rewrite what we found. So we have phi outside of R is C0 out by R plus C1 out, and phi inside of R is C0 in by R plus, these are vectors, this is magnitude of a vector, and then C1 out, C1 in. So now the first boundary condition that I would say is that, you have a charged sphere here. The charge is on the surface, but let's say you're very far away. You're very, very far away at this point P, right? Where your distance R from the center is much, much greater than the radius of the sphere itself. So then it would look like this sphere would look like a point charge from that distance. So its field would simply go down as, kq by r square, and we know that as you go farther and farther, the electric field should become weaker and weaker, right? And so we know that as, r is in r greater than r region, as r goes to infinity, we need phi to go to 0, right? So so by using that, we can look at, phi out. So phi out for r much, much greater than, r, and r going to infinity, we basically have this to go to 0. So that means this should go to 0. That means, C out by something where r is going to infinity plus C1 out is equal to 0. And because this has a large number in the denominator, this is very tiny contribution. So then that means C out is C1 out is equal to 0, because we at very far away from the surface of the conducting sphere, both the potential and the electric field should go to 0. That's what the common experience would tell us. Now then, let's talk about another boundary condition that would be r less than r, right? So here we have a conducting sphere, right? So the surface is, the charge is only on the surface. So there is no charge inside, and if there is no charge inside, there is no electric field inside. So here phi, we know that inside a conductor it is constant, right? So if the phi inside the conductor is constant, that means if you look at the expression for this phi in, we cannot have this first term, because inside the conductor there is no charge, electric field is 0, and so the potential is constant, but this is varying radially, so that term has to be 0. So then by the condition that phi is equal to constant inside the sphere, we can say that C0 in should be 0, right? And then let's look at another one. So let's say this is the conducting sphere. There is charge on the surface, and let's say you're going from a point inside to a point outside, right? Let's say this is R1 and this is R2, and along this path I would like to integrate R1 to, this is not a surface integral, this is just a line integral of E dot dl from R1 to R2. Then I can see that if I'm going to reduce, this is the dl, right? If I reduce dl to almost 0, right? So that R1 is just inside and R2 is just outside. If I reduce that dl to 0, you can see that because E is finite, E is not infinity, E is some finite value near the surface. So in the limit that dl goes to 0, because E is finite, this integral goes to 0. And you know that this integral is related to the potential. So the potential E is equal to negative grad phi, right? That means, phi at R2 minus phi at R1 should be equal to minus R1 to R2 E dot dl. But we have seen that if I make this dl to be very tiny, if I reduce the distance between the point outside and inside, so that I'm just going, just considering a point that is just inside the sphere and a point that's just outside the sphere, then I can reduce this dl to almost 0. And E is finite, E is not infinity, E is finite everywhere. So this product of E dot dl would go to 0 if I make dl very small. So then from that argument, we can see that this should be 0, or phi outside, right, should be equal to phi inside at the boundary, right? So at the boundary, we have phi out of R should equal phi in of R, because the difference between those potentials is 0. So we have determined from the first two boundary conditions, we have seen that phi outside of R was equal to C0 out by R, and we have seen that phi in of R was equal to C1 in. So now if I look at phi out at R, that should be C0 out at R, right? And this should be equal to C1 in, which is phi in inside R, right? So now we have a link between C1 in and C0 out. So if we know one of them, then we can determine the other. So we only have one unknown left. We started with 4 unknowns, right? We started with 4 unknowns: C0 out, C1 out, C0 in, and C1 in. Then we applied the first boundary condition, that is, at infinity the potential should go to 0. Using that, we knocked out one of the constants, so we had 3 left. Then we made the argument that inside the conductor phi is constant, so we knocked out another constant. And then using the boundary condition that the potential should be continuous, we found out a relationship between C1 in and C0 out. So now I uniquely need to determine, if I determine one of these, then I should have no problem determining the other. So to do that, now let's look at the electric field just at the surface. So I'm drawing a part of the surface of the sphere, right? And I'm going to consider this more or less flat part here, roughly, or it doesn't even need to be flat. Even if it is curved, you can still get the same answer. So now I can take a Gaussian pillbox around the surface. So I can take a Gaussian pillbox around the surface, right? And let's call the surface S. So I can get the surface integral of E dot dA. Now, if I reduce the thickness of this surface, so the thickness goes to 0, then the contribution from the sides don't matter. So essentially, then I would have this to be an integral over the top face, right, of E dot dA, and plus over the bottom face of E dot dA. So in general, I can write dA as unit vector n times dA. So for example, if you're on the top, your electric field would be pointing upwards, right? And we do know the direction of the electric field because the surface as we have seen, the electric field on the surface of the conductor should be perpendicular. That's one of the properties that we discussed while discussing conductors, right? So we do know the direction of electric field, and the area element depends upon how the surface is curved. So the area element here would be pointing in a different way than the area element here. So in general, we can write it as NdA, right? So then I would have this to be equal to E top dot N top dA plus E bottom dot N bottom dA. Right, the bottom area vector need not be equal to the top, because here in the simple case of the flat sheet, this is pointing downwards, this is pointing upwards, so there could be different directions there. So then here in case of the surface, we do know that they are in case of the spherical surface, we do know that the top is n, and n bottom is minus n. In case of spherical polar coordinates, this would be r, and this would be minus r, and n in general for any surface. So then in case of a sphere, we can write this as an integral of E top dot r minus E bottom dot r dA. Or I can simply write this then as E top minus E bottom dot r is equal to r times dA, right? I'm just approximating this, I'm accumulating the terms in this integral, right? And we're basically trying to establish a boundary condition for the electric field at r is equal to r in the charged conductor, so that we can figure out what the fourth constant is. So we have E top minus E bottom dotted with r times dA. Now on the surface, the pillbox that I'm taking, I can, if I start with a pillbox that looks like this, I can make this thickness go to 0. I can also make this radius go to 0. So I'm reducing this this area of this pillbox, so that I'm limited to just a point above and point below. So I'm making this Gaussian pillbox, I'm shrinking it down to a small point. I'm making the box thinner and thinner. So I'm not only reducing its thickness, I'm also reducing its area, right? So then if I make it down to a small area, right? If I make it down to a small area of dA, then I can replace the integrand for that small tiny this tiny dot as E top minus E bottom dot r times dA. So we're saying that this integrand itself, that is, we're limiting the integration to a tiny area. So the overall integral would be this, right? So, and that gives us E dot dA, that is the flux, the total flux. And we know that the total flux, E dot dA, from Gauss's law, is equal to the total charge enclosed divided by epsilon naught. And here we have that E dot dA, that is this. So I have E top minus E bottom dot r times dA is equal to the total charge enclosed is sigma times dA, right? That's sigma is the surface charge density. So divided by epsilon naught. So I have these dA's cancel out. Then I can write this E top minus E bottom dot r as sigma by epsilon naught, or I can write it as E top minus E bottom is equal to sigma by epsilon naught r. So the way we can write this is, here we are essentially, while doing this, we are essentially taking only the perpendicular component of the electric field, because we are looking at the electric field at the top and bottom. We don't have any contribution from the tangential part of the electric field, and we do know that the line integral or the loop integral of E dot dl is 0, right? We know that loop integral of E dot dl is 0. So that's how we can say that this E top minus E bottom in this case is completely radial, because there is this radial symmetry in the case of a sphere. So now we came up with this, but we know that E is equal to negative grad of phi. So then I can write this as this condition then as minus grad phi top minus of another minus grad phi bottom dot r is equal to sigma by epsilon naught, and I'm going to rewrite this on the next slide. So I have grad phi top plus grad phi bottom is equal to sigma by epsilon naught, and here I have it dotted with r. So I'm dotting this grad with r, so I'm going to take only the r component of the gradient. So, or I have minus dou phi top by dou r plus dou phi bottom by dou r is equal to sigma by epsilon naught. So this is the other boundary condition. So our first boundary condition, so we started with del square phi is equal to 0 for r less than r and r greater than r, and we found out a general solution by making an argument for spherical symmetry. We saw that in general phi of r is equal to c0r plus c1, and then we saw that then outside you would have c0 out by r plus c1 out, and inside again these are functions of vectors. So C0 in by R plus C1 in, right? And then we set out to find what these constants. We had 4 constants, so we set out to determine those 4 constants. So the first boundary condition we took was at r is equal to infinity, phi goes to 0, and the second boundary condition we had was for r less than r, phi is equal to constant. And from this we ruled out 2 constants, right? We ruled out C1 out and we ruled out C1 in. So then we had these 2 constants left, and then we correlated these 2 constants by looking at r is equal to r. We looked at the potential just inside and just inside and just outside the sphere, and we saw that phi is continuous, right? So phi in of at r is equal to capital R was equal to phi out for r is equal to capital R. So we related these two, C out, C0 out, and C1 in through this. So it is enough to determine one of them. So then we set out to find another boundary condition. That was the 4th boundary condition. And to find the 4th boundary condition, we essentially found that E top minus E bottom is equal to sigma by epsilon naught r, because of the Gauss's law, and then you have here this one, right? So now we know what phi out and phi in are. So in general, I was talking about top and bottom because I was talking about the top and bottom of the Gaussian pillbox. But the top of the Gaussian pillbox, so this is the sphere, this is the surface of the sphere. So the top of the Gaussian pillbox is outside, and the bottom of the pillbox is inside. So this phi top corresponds to outside, and this phi bottom corresponds to inside. So I can simply do dou phi, and this is all at r is equal to r, right? Because we are considering all this happening at one particular r is equal to r, right? So at the boundary. So dou phi out by dou R is simply minus C0 out by R square, whereas dou phi in by dou R is equal to 0, because phi in is only C1 of n. It's a constant. We ruled this part out because inside the conductor, the potential is constant because there is no electric field inside a conductor, right? And then, so now, then by combining these two, I can plug this in here, plug that in there. I can see that dou phi out by dou R at R is equal to R. The second term is essentially 0 because this is 0, is minus C out by R square. So this should be equal to sigma by epsilon naught. So then I can write then this as, C out should be equal to minus sigma R square by epsilon naught, right? So now I have determined C out, right? So then I can go back and see the expressions, right? So for phi phi out, right? For phi out, we would have C0 out by R as the solution, and C0 out came out to be sigma R square by epsilon naught time divided by R, right? So you see the 1 over R dependence, right? So if I multiply by 4 pi here and 4 pi here, this gives me the total charge because sigma is only on the surface, right? So then I get the total charge because this is the surface area and this is 4 pi epsilon naught R. So this is kq by R, right? And then phi inside is equal to C1n, and we have seen what that C1n should be. It should just essentially come out to be from what we had found out between the relation between C1n and C out, right? We had this relation. So I know the C out. So C1n should be C out by R, right? That is sigma R squared by epsilon naught by R. So that's cancelled. So you have sigma R by epsilon naught, right? So then if you multiply by 4 pi R and multiply by 4 pi R up here, then you have 4 pi R square. So again, this becomes the total charge divided by 4 pi epsilon naught. It's the same charge Q, 4 pi epsilon naught R, right? So this is simply Q by R, which is constant because R is a constant. This is the radius of the sphere, right? So using these boundary conditions, then we were able to figure out. So we started with the Laplacian equation, and we used that to figure out what is the solution to this problem, and this negative sign here, this negative sign has disappeared here because remember that originally we had absorbed a negative sign into C0 because when we integrated here, when we integrated here, I had absorbed this negative sign in there explicitly. But if I didn't do that, then essentially here you would get positive, right? So this negative is an artifact of me absorbing the negative sign initially. So ultimately this is positive. If you didn't absorb that sign into C0, then that would be positive. So that's why these are positive. So note that. So to summarize, what we had done is we have taken a charged sphere. The charge is only on the boundary, right? And then we saw that del squared phi is equal to 0 inside and outside, right? And then we found out a general solution that was C0 by R plus C1, and we wrote this for inside and outside, and then by using boundary conditions for R greater than R, when R goes to infinity, phi goes to 0. So phi out goes to 0, excuse me, as R goes to infinity. And the second condition was for R less than R, phi is equal to constant. Phi in was equal to constant. And then the third condition was at R is equal to R, phi in of R is equal to phi out of R. And then the fourth condition, we use the Gauss's law, and then we saw that we saw that at R is equal to R, E top minus E bottom dotted with, in general, the normal vector is equal to sigma by epsilon naught, right? And so using this, we saw that minus dou phi top by dou n plus dou phi bottom by dou n was equal to sigma by epsilon naught. So this was our fourth and final boundary conditions. We had four constants, 2 for in, C0 in, C1 in, 2 for out, C0 out, C1 out. And using these four boundary conditions, we figured out what these constants should be. And at the end of the day, we were able to see that phi of R is equal to Q by R and Q by R for R less than R and for R greater than R. And from here you can essentially get what the electric field would be by taking the gradient of phi. So the advantage of this method is, so here, when we were solving an infinite sheet or something like that, the area vector was trivial in the sense one was pointing up, one was pointing down, and we could only do it on a flat surface. But here, you don't really need a flat surface. You can also apply this to any curved surface in general. So then basically we can use a similar approach to solve many problems. So this is how we would solve the Laplace's equation and figure out the solution for phi using the differential equation method and the boundary conditions.